So in Chapter 11, we get to talk about ANOVA, which is called One-Way Analysis of Variance. So we use one-way ANOVA when we want to compare the population means across more than two populations. So maybe you want to compare the mean mileage of 4 different brands of tires, or compare the mean weight loss of 5 different diets. What you do is you take a sample from each of the populations. So you'll end up with 4 or 5 samples. Now, it shouldn't be surprising that the null hypothesis would be that the first mean equals the second mean equals all the way up to your last mean, or that all the population means are equal. That makes sense, right? Because that's the same as what we've been doing on every single one. The alternative is slightly different here, because if you look at the means are all equal as the null, the opposite of that is that not all the means are equal, which we actually refer to it as at least one population mean is not equal to the others. So let's actually look at a new page. Let's put a new page in here and look at what this can mean. So the null hypothesis is that the first mean equals the second mean equals the third mean equals the fourth mean. And let's consider, so if the null hypothesis is false, what are the options? Now this one we're just assuming 4 different populations. You'd have similar things for 5 or 6 populations. So what are the options? Basically it's not all the means are equal. But there's different ways that this could actually play out. The first one that people usually say is they say, well, that means that all the means are not equal. Which might seem like it's saying the same thing, but it's not. There's a slight English difference here. This one says not all the means are equal, so not all of them are the same. But this one says all the means are not equal, which means that the first mean is not equal to the second mean, is not equal to the third mean, is not equal to the fourth mean. So they are all different. Now, if that happens, then the null is certainly going to be false. But it's not the only way the null could be false. You could also just have one that is different. Perhaps the first mean is not equal to the second mean, but the second one is still equal to the third one, still equal to the fourth one. If even the first one is not equal to that second one, does that mean that the null is false? Yes, because the null is that they're all equal and this one be true. Or you could have the first mean is equal to the second mean, but that is not the same as the third and the fourth. Oh, that's written wrong. We have only one difference, so like the second one could be equal to the third one, and that could be not equal to the fourth one, etc. So maybe just one is different from all the rest. Or maybe you could have 2 that are different. And that might look like the first 2 are equal, and the third and fourth one are equal, but those 2 groups are not equal to each other. Or maybe it's like the first and fourth are equal, but that's not the same as the second and third, etc. So there's lots of different situations that could actually happen here. But no matter which one you choose, the null hypothesis that they're all equal would be false. What I need you guys to remember is that the alternative is that at least one mean is different from the others. So the null is that they're all the same. The alternative is at least one is different. That might mean that one's different, or 2 are different, or they're all different. You don't actually know. All you know is that at least one is different. So with that, let's go back to our previous page. So the null, they're all equal. The alternative is at least one is not equal to the others. Oh, sorry, I forgot. This is, I put a space in here to actually do that next time around. So we just did that. That's what all the possibilities are. So let's look at some theory. So let's remember that there's variability in samples taken from your population. So even if all of our population means really were equal, you'd expect to see some difference between the sample means, right? Your sample means won't be exactly the same. Okay, and so it turns out that observed differences between your sample means can be caused by two things. They can be caused by true difference in your population means, but they can also just be caused by sampling variability, because based on which sample I get different sample means. So what we want to know is we want to know if the observed differences among the sample means are due to just the chance sampling variability of which sample I picked, or if the differences are statistically significant, meaning that the population means are different. So I have two different sets of box plots here. So in my first set of box plots, we have 4 different groups. And if you were to look at these groups, and these are from the samples, do these groups seem fairly similar? Let's look at the center. Are the centers fairly similar? They're not exactly the same, but kind of similar. But when we look over here on B, are these centers fairly similar? Definitely not, right? So in A, even though there's some differences in the centers, there's also a lot of difference just within each box plot. So each group has quite a bit of variability, or quite a bit of spread. And so you'd kind of expect that your sample means to kind of go up and down a bit based on which sample you pick. But over here, each group kind of has a very small spread. And so you can see that the sample means not just kind of going up and down within the box plot, it's the whole box plot itself is truly moved. So our comments on our first one, the variation within the groups. Now when we say variation within the groups, we mean how big is the spread within the group. So the variation within the group seems big enough that the differences in the means are likely just due to sampling variability. And the population means are probably the same, or at least fairly close. But for B, the differences between the group means, so here's our different means. Notice the actual dot in there, that's the actual mean instead of the median. The line's the median, the dot's the mean. So the difference between the mean seems big compared to the variation within the groups, or the spread of each group. And this means the population means are probably different. So again, this is kind of our theory here. We want to compare the variation between the groups and the variation within the groups. And they came up with an interesting way to do it, which again seems very different from what we've done so far. And as we go through this, you don't necessarily have to memorize all of this until we get to the next page. Okay. It's just to kind of explain. So we have 3 sources of variation to consider in the data. It's what's called groups, or treatments, depending on what you're thinking about, which is the variation between the actual group means. The error, or sometimes called residuals, is the variation within the groups, and total is just total variation in the data. You have all of these little dots, each dot represents a point, but they're not all the same, there's just variation between all of these points. And then you have what's called sum of squares, okay, which is the sum of the squared deviation. So this is how much the data deviates from the predicted values or means. So like SST, T would be for total, G would be for group, and E would be for error. So total, group, error. So the total measures variation in the data around the overall mean. So come up here, notice this dashed line. This dashed line here is the overall mean. And so you take each point and minus the overall mean. That's the variation between the point and the mean. And the next point minus the overall mean, next point minus the overall mean. So that's variation of data around the overall mean. And then SSG is variation of the group means around the overall mean. So notice this little blue line. That's your group mean. So you take each group mean and see how far it is from the overall mean. And then SSE, sum squares for error, is measurement of each observation around its group mean. So this top dot gets compared to its group mean, and each of those little dots gets compared to its group mean. And over here, each of these little dots gets compared to its group mean. So you have, each group has its own little group mean. And it turns out that if you add SSG and SSE, you'll get to SST. Okay, for degrees of freedom, we have different degrees of freedom. So each of these different things has its own little degree of freedom, which you don't really need to worry about finding them or thinking too much of that. Mean square basically measures the same thing as sum of squares, but we're going to scale it based on our sample sizes and number of groups. Because if you have really big samples, you'd expect to have more variation. Or just because if you're truly taking each value minus the mean and squaring it, so the positives and negatives don't cancel each other out, then the more values you do, the bigger that sum of squares gets. And so you have to scale it based on the sample size. And so for mean square, you always just take the sum of squares divided by its degrees of freedom. So like the mean square for total would be the sum square of total divided by degrees of freedom for the total. Now the test statistic, this is the first thing that I want you guys to understand here. We need to measure the variation between the groups compared to the variation within the groups. And the way they decided to do that is with this test statistic. F is going to be the mean square group over mean square error. So I want us to figure out if the population means are different, what kind of F values would you expect? So again, F is equal to variation between groups over variation within groups. So again, if our population means are different, then the variation between the groups should be very big. Your groups should be far apart from each other. And so this will kind of be a big value on top. And you need the variation between the groups. The differences in your population needs to be really big compared to the actual spread within your group. So we kind of want a bigger number divided by a smaller number, meaning we'd be looking for bigger values. So this means if the population means are different, we would expect big F values. That part is something you should remember. So what we're going to do is look at a couple Excel simulations here. So the one listed doesn't work anymore. So these are ones that I made. So this is just to kind of show you what could happen. You'll notice up here I have population parameters, so I can set what's going on with the actual population. So notice here I have 4 groups, and each one has the exact same mean of 15 and same standard deviation of 5. So I'm going to put here some actual just like little dot plots, okay, where you have a dot for each value when I take a sample, and then a box plot. So it's about the same thing, but they just look a little bit different. And then up here you can see the sample summary data. So I took sample sizes of like 29, 25, 27, 22. I have my means and my standard deviations. Now notice here where I have exactly the same population means, are my sample means exactly the same? Okay. They're not. They're 15.8, 14.0, 13.2. That one is 15. But they vary. And that makes sense because we don't expect our sample means to be exactly the same as our population means. And even my standard deviations, they're all each pretty close to my overall standard deviation of 5, but not exact. And that's always important to remember, is that when you take your sample, it's going to give you stuff similar to the population, but not exact. Now I want you to watch this. Okay, so just look here, okay, at my plot. What happens if I take a different set of samples? So I can take a different set of samples easily. And notice those plots changed. And did my sample means change? Okay, my sample means changed as well. But let's look at these box plots just so you can get an idea. If I keep changing this, I get different samples, but are my group means all fairly close to each other? And when you look at your box plots, like they all seem pretty close to each other, especially considering the overall spread. Even though it changes a bit each time, they all seem fairly close to each other. But I could change this. I can make one of the means a lot higher. And notice now when I take a sample that that third group that has a much higher mean is suddenly much higher up there, isn't it? But if I change all of these standard deviations to maybe like 20, do these box plots, looking at the box plots, do the centers seem all that different anymore? The centers don't even seem that different anymore because my standard deviations are so big. Or the variation within each group, is so big that the difference in those group means just doesn't seem quite as noticeable anymore. Okay, so now that we've looked at that, let's go to a second one. This one's different. So this is our actual sample data up here. So I can change what the mean is for each one, the sample size for each one, and the standard deviation for each one. And then this is an actual calculator. So this calculator will go through and tell me everything that's normally in an ANOVA table, ending with a p-value and a test statistic. And right here, you can see I have some different things for you to look at. The first one is mean square. So you have mean square for your group and mean square for your error. And you see your f-test statistic, and remember, if the population means are different, we'd expect really big f-test statistics. And of course, like anything else, if our population means are different, we'd be expecting a really small p-value. So let's try some different values. Notice right here, okay, do my means seem pretty similar? Looking at the box plot. They seem fairly similar. Notice I have a big p-value of like 0.4, so I would feel like I'd fail to reject the null, and I say I don't have any reason to think that my means are different. And notice the variation between my group and error seems pretty similar. And f is 0.82, so that's pretty small. So let's make our means a little bit separate. So let's move the mean for my first group up a little bit higher. And notice as it gets higher, okay, that variation, or the mean square for the group, the difference in the group, starts to get really big. And my f-test statistic is getting really big, and my p-value is now so small I can't see it anymore. Okay? And so you can see that these population means are probably, at least one is different. What happens though if I increase the standard deviation? If I increase the standard deviations, what's going to be happening here? Look at the box plots. Does it seem like there's such a big difference in the means anymore? Okay, if I'm increasing the standard deviation, so I'm increasing the variation within the groups, now it kind of looks like those means are almost the same again, right? And the group and errors are more similar. My f-test statistic is 3, so it's a lot lower, and my p-value is only 0.05. So it still kind of shows that there's a bit of a difference, but it's not nearly as noticeable. And like here at this point, my p-value is 0.16, so I'd probably say I don't have any reason to think that my population means are different. So it's all based on how is the spread or the standard deviation within each group compared to the difference in the means. So here's our official page for an ANOVA f-test. We use this if we want to compare several population means, meaning more than 2. Our assumptions are that the population variances are all approximately equal. Now really, when they say approximately equal, we just mean that the biggest isn't more than 5 times larger than the smallest. So they're all, there's not one that's hugely different. The populations are all approximately normally distributed. Really that just means like kind of mound-shaped and fairly symmetric. So not even really bell-shaped, but just kind of a mound like this is good. and the samples are independent. Now this one, we're usually not given enough to actually check this on the ANOVA test, so we're not going to check it every time like we have been doing. That's just what they would be. The null is that all the population means are equal. The alternative is that at least one of the means is different. You have your test statistic and degrees of freedom, but you're never going to calculate those by hand. We're going to use our output. Now the p-value, this is different from what we've been doing. The p-value is always the area to the right. The reason why is on our previous page. Remember, we said if our population means are different, we get big p-values. And so this is one where it actually never changes. It's always going to be the area to the right. Okay. Now for an F table, F distribution, you do have to have two different sets of degrees of freedom. But again, we're not even going to worry about the tables. We just use our computer output. This is a typical ANOVA table, so you can kind of see what's on here. We have degrees of freedom, sum of squares, mean square, our F test statistic, and a p-value. And you have what's either going to be called groups or treatments, depending on which software you use, and an error, and then the total. You can see on here how they're all related, so like the F test statistic is mean squared group over mean squared error, but you don't need to memorize any of this. You don't have to calculate any of it by hand. And the last thing is what's called coefficient of determination, R squared. R squared is sum squared groups over sum squared total. Yeah, I will make you calculate this by hand just because most computer softwares don't necessarily always output it, and that's pretty easy to do. Okay, so R squared tells us the percentage of variation that's explained by differences between the groups. And the rest of the variation just comes from individual variation of people within each group, just like the differences between each person. But so R squared is the percent of variation we can explain by which group you are in. So let's maybe write that, by which group you're in. Let's try an example. This is really what real life analysis is like. We've been making you guys do things by hand. In real life, you have a computer software that does all of it. What you have to be able to do is check assumptions, write down hypotheses. You even have to be able to pull out certain things from the computer analysis. Like if you're ever reporting results, you would always tell people like what all of your sample means are. That would be something they'd want to know. Okay. Or they might want to know what your F test statistic is and your p-value. And so you always tell them your test statistic. You always tell them your degrees of freedom. You tell them your p-value, things like that. So you pull numbers out of the table, you write hypotheses, and you interpret your results. That's what you actually do in practice. So in this example, a sample of 134 students was taken. They were broken into groups based on how many Facebook friends they have. And they were also, separately from that, given a social attractiveness score. And we want to know, is there a difference in the population mean social attractiveness score based on how many Facebook friends the person has? We want to conduct hypothesis tests to find out, and we'll also find and interpret R squared. So you'll see here our results for each of these groups, for number of friends. We have our sample size, our sample mean, and our sample standard deviation. And we have our box plots. Now looking at this, do those seem like the means are probably the same or different? I'd probably guess like these three are probably about the same. These ones might be different though. I'm not too confident about them being the same. But let's go ahead and do our test to find out. First of all, we know this is going to be an ANOVA test because we have more than 2 samples. And I'd probably go ahead and just choose alpha equals 0.05. I told you, you don't have to check the assumptions on these because I usually don't tell you enough to know. So we'll just skip to our hypotheses. The null will be that all the means are equal. And the alternative then is that at least one mean is different from the others. So this is what our ANOVA output looks like from the computer. Each group, I have the group names, I have the mean, sample size, and standard deviation. Then you have this ANOVA table. Notice they have SS, that would be sum of squares, degrees of freedom, mean square, an F test statistic, and a p-value. Now notice this does say treatment, and we're used to calling it group. Treatment just means the same thing as group. So the two things I'm going to ask you for every time is your F test statistic and your p-value. Sometimes I might say, what's the sum square of error, just because I want you to be able to pull it off from the table, but that's really just a matter of saying SS sounds like sum squares, here's error, and tell me what the number is. So that means I get to say, what's my test statistic? F equals 4.14. That's the easiest thing we've had so far. And what's my p-value? My p-value is 0.0034. So ANOVA is really super easy. Okay, you take this p-value, compare it to alpha. Alpha is 0.05. This is 0.0034. That seems small. So this is a small p-value. So we'll reject the null. And we would say something like, we found very strong evidence that there is a difference in the population mean social attractiveness score based on which group they are in for at least one group. So we're not saying all the groups are different. We're not even saying which groups are different. We're just saying for at least one of these groups it's different from the others. And finally they said find and interpret R squared. So R squared, the formula for that is sum squared group over sum squared total. So coming up here, which one do you think would be SS? Or sum squared, I would guess it would be the SS ones. So for the group, that's called the treatment one. So that would be 19.890. And sum squared total is 174.757. Which is 11.38. Actually, it's 0.1138. And what does this mean for us? Okay, this means, so remember I said it's the percentage of the variation you can explain based on which group they are in. So we could say 11.4% of the total variation in social attractiveness scores is explained by which Facebook group they are in. The rest of the variation is explained by individual variation that occurs naturally from person to person. So this one tells us 11.4% of that total variation in the social attractiveness scores is based on which Facebook group they're in, or like which group of how many friends you have. The rest of the variation is just that individual variation that happens from person to person. This is actually a really low R squared value. Okay? This is telling us that which group they're in really doesn't do very much for their social attractiveness score. 11%, that's really not very high. And that means that just that natural variation from person to person changes the scores a lot more than which Facebook group they're in. So we can do what's called pairwise comparisons. So the analysis of variance, or ANOVA, only tells us whether or not the means of the populations are equal. If they're not all equal, ANOVA doesn't actually tell us where the differences are. What we can do is what's called pairwise comparisons. They can tell us which means are different and by how much. Now you should only use these if you've already done an ANOVA and the null hypothesis is rejected and you know at least one of the population means is different from the others. So when we do an ANOVA test first and then we look at a pairwise comparison, we call this a post hoc analysis. And our book talks about ways to do like confidence intervals for pairwise comparisons. Okay. Really, we would just look at the megastat analysis, and I'll just have you kind of do this once or twice. We're not really focusing on it. So in this example, we have the megastat output for pairwise comparisons, and we want to know which pairs have significantly different means at the alpha equals 0.05 level. So you'll see the way they do this is they set up this comparison. So they have each of the groups of friends across the left and across the top, and the p-value to compare each different pair. So all you have to do is you go through and you find any p-values that are less than alpha. So if alpha equals 0.05, we have this 0.0020, 0.0007, and 0.0058. Looks like that's it. So what this tells us is that the mean for our 502 group is not equal to the mean for the 102 group. And let's see, this one has the 302 and 102. So the mean of 302 is not equal to the mean of 102. And the last one is 302 and 902. So the mean of 302 is not the same as the mean of 902. Let's look at our little dot plot over here. So notice that 102 seems to be kind of different. Oh, that's probably because 102 is pretty low. And so it's going to be different from 3 and 5 because they're a little bit higher. But it's not too different from 7 or 9. And then the 3 is really high, the 9 is kind of low, so they're statistically different as well. So let's try one more. The lengths of flowers in millimeters are compared for 3 species. And we want to know, are their mean lengths the same? Conduct an appropriate hypothesis test, find and interpret R squared. Okay, so you can see our ANOVA here. We have the groups of blue, red, and yellow with our sample means, sample sizes. Now, I guess that's actually Baha'i, not blue. If I had done this and I wasn't having to do something that was really official, and let's say I got a small p-value and I know that they're different, I could probably just look at this and be like, oh, obviously the Baha'i is a lot longer than the other ones, if that's what I'm interested in. But officially, we'd go through and do an actual post hoc analysis to see which one's different from the others, etc. Okay. I might notice looking at this dot plot that even without looking at my ANOVA table, I'm going to guess that my group means are different, right? Those means seem to be very different compared to the variation. And I could tell you that Baha'i seems to be the longest, red is kind of in the middle, and yellow is the shortest. So on your ANOVA table, remember that this treatment row, that's the same as saying group. And we go through and we always check the same things. We check, okay, let's use alpha equals 0.05. We're going to write our null. Last time I wrote it in words, this time let's do some symbols. So I might say the mean of B for Baha'i is equal to the mean for red is equal to the mean for yellow. Then for the alternative, there's not really a good way to write this in symbols. We're still going to say the opposite of the null is that at least one is different from the others. So again, at least one population mean is different from the others. Now that you have your hypotheses, the next step is your test statistic. Well, the reason I love doing ANOVA is you just say test statistics. I just look at my table. That is 259.12. That seems pretty big, right? That's probably going to give me a small p-value. And my p-value is 1.9 e to the negative 27. So this means 1.9 times 10 to the negative 27 is what that e means. That's a very, very small p-value, right? So this is a small p-value. We'll reject our null. And we would say something like, we have, now that's a very small p-value, so I'm going to say extremely strong evidence here. We have extremely strong evidence that at least one of the population mean lengths, because we're talking about flower lengths, is different from the others. Let's see. So I have R squared is supposed to be sum squared groups over sum squared total. So my groups is this 1082, the total is the 1189. So 1082.8724 over 1189.4381, which gives me 0.91. So this now means that we can explain 91% of the total variation in lengths by which group or species they are in. That is a really big R squared value. That one's really nice. That's saying most of the differences in their lengths is based on which species they're in. Which is pretty cool, because that means if you know the length, you could probably even go backwards and guess the species, things like that. So that means the species really affect the length of the flower. And there's just this final note that, again, remember, our alternative just tells us at least one is different. It doesn't tell us which one is different. We'd have to go through and do a post hoc comparison if you want to know officially. So one more. A company's testing 3 different types of gasoline to see if they have an effect on gas mileage. Let's conduct a hypothesis test at alpha equals 0.01 to determine if the type of gasoline has an effect on the mean gas mileage. So let's do 0.01 like they told us to. The null will be that the mean for type A equals the mean for type B equals the mean for type C. I have A, B, and C because that's what it has here on my little table as the group names. And the alternative will be at least one population mean is different from the others. Then you need to look at your test statistic. So on the test, I do things like ask, what's your test statistic? And then all you have to do is tell me F equals 12.74. So there's F. And here's my p-value right next to it. My p-value equals 0.00 or 0.0011. Now, even though alpha is 0.01, that p-value 0.0011 is still smaller, right? So we still have a small p-value. And we'll reject our null hypothesis. And we would say something then like, we have very strong evidence that at least one of the population mean gas mileages is different from the others, or from the other gas types. So at least one of them is going to be different. And we'll calculate R squared. R squared is almost kind of our way of telling us how practically important it is. So your p-value tells you how sure you are statistically, and the R is kind of one of our first measures we've seen of how practical it might be. So R squared, again, sum squared group over sum squared total. So our sum squared for groups is 17.049 and 25.007. So 17.049 25.077, which is 0.6798. And then we say something like, we can explain 67.89% of the total variation in gas mileage based on which gas type they were using. That's not too bad. It's not as high as 91%, but it's still not too bad. So about 70% of the variation is based on which gas type you are using, which means that it is influencing it a fair amount.